Hello and welcome to Chegg's Stoichiometry Live Office Hours. If this is your first time joining, welcome. We're so glad to have you. Chegg has put these office hour sessions together to help you learn more about the classes you're taking and to help you succeed in those classes. If you're coming back, welcome. We're so glad that you're back, and we hope that you join more office hour sessions throughout the week. I'm Allison. I'm going to be your instructor today. I have TA'd for chemistry for about a year, specifically some organic chemistry and then some regular chemistry. And then I've been a student learning assistant for nursing chemistry. I also tutored in organic chemistry in high school, and I've done some other personal tutoring for calculus. So it is so glad to have you guys, and I hope you learn lots this session. I encourage you throughout this session to ask questions of your own. That's what I'm here for, is to answer the questions that you have. So if you have any questions, type those in the chat of wherever you're streaming from. So YouTube, TikTok, whatever you're coming from, type those questions in the chat and I'd be more than happy to answer them for you. I'm going to get started with a few questions that I wrote so that we can kind of warm up. But remember, throughout this live stream, ask those questions that you have. So first, we are starting out with, in the combustion of C9H18, how many milligrams of C9H18 are needed to fully react with 60 grams of oxygen? So first step in this, if you know, I'm going to ask several small questions for each problem throughout the live stream. If you know the answers to those questions, type them in the chat to lock in your answer and check your work to make sure you're understanding what we're going through. So for this, we are going to first need a chemical equation. We're going to need to balance that. When we combust anything, it's always going to be what we're given that's in the combustion reaction plus oxygen, which is O2. We never find oxygen alone, yields carbon dioxide plus water. It's always, if your thing you're combusting is made out of carbons and hydrogens and you're reacting with oxygen, you're always going to end with carbon dioxide and water. That's one of the rules of combustion. If you've learned about different reactions, you'll know this. If not, that's okay. You'll probably get there in your chemistry classes eventually. So now we need to balance this equation. I'm going to give you guys about 15 seconds of a head start to balance this equation before I do. Then we'll work through it together. So if you get that answer, type it in the chat to lock in your answer. You've got about 10 more seconds. All right, 3, 2, 1. Okay, so with combustion and balancing equations, I've gone over this before, but I'll go over it again in case this is your first time. I always start with carbons. That's what I was taught, and that is what has been the easiest that I've seen to this day. So I start with carbons, and I have 9 carbons on the left. So I want to make 9 carbons on the right. I then look at hydrogens, and I do that because I want to leave my oxygens to last because oxygens are alone. So if I change the amount of oxygens that I have, that's not going to change how much of the other elements I have. So that's why I go carbons, hydrogens, and then oxygens. Then I'm going to hydrogens, and I have 18 hydrogens. So I'm going to put a coefficient on this water that's going to give me 18 hydrogens. So 9 times 2 is 18 hydrogens. And then last, I'm going to balance my oxygens. So I have 9 times 2, 18 oxygens here, and 9 oxygens here, which is 27 oxygens, which is not a whole number. So I would put 13.5 because 13.5 times 2 would give me 27 oxygens. But I need whole numbers when balancing a chemical equation. So I'm just going to multiply all those coefficients I just wrote by 2. So my final balanced equation would be 2C9H18 plus 27O2 yields 18CO2 plus 18H2O. If that made sense to you guys, send a thumbs up in a chat or some sort of comment. If you're struggling with something, type that in the chat and I'd be more than happy to go through in more detail whatever you guys are struggling with. Now, we need to figure out how many milligrams of C9H18 are needed to fully react 60 grams of oxygen. So we always start with what we're given, and in this case, we're given oxygen. So I'm going to write 60 grams of O2 to start. And then I want to go from grams of oxygen to milligrams of C9H18. So the way that we do that is through a molar conversion. And I'm going to give y'all about 10 seconds to kind of think about or write out, if you know, that thought process of how we're going to get from the grams of oxygen to the milligrams of C9H18 using that molar conversion. If anybody knows, type it in the chat so that you can lock in your answer and we can check our learning and how much we're understanding. I'm going to give y'all about 5 more seconds. All right, so we first need to find the molar mass. If you said that and thought that, you're absolutely correct. We need to find the molar mass of our oxygen and our C9H18, and then we're going to use those coefficients in the chemical equation that's balanced to also get from our grams to our milligrams. So if you said either of those things, great job. You're absolutely correct. So what I want to start with is finding those molar masses. So I'm going to scroll over here. We're going to do our molar masses. All right, and let's start with oxygen. We'll do a quick little run through of how to do this. I've gone through it in some other sessions, but if you're just now joining in, I want everyone to understand. So this is how we find the molar mass. We count how many are in the molecule of each element. So in this molecule of O2, we have 2 oxygens. So we're going to do 2 times whatever molar mass you can find on the periodic table for oxygen. If you look at the periodic table for oxygen, you're going to see it has a molar mass of 16.00 grams per mole. Some of the periodic tables, if you have more significant digits, they might be a little different, but this is just what I always learned with 16. Make it simple, keep it easy. And so if we multiply that across, we're going to get O2 has 32.00 or just 32 grams per mole. Now we are going to go to C9H18. Since we kind of ran through how to find the oxygen, does anybody have any ideas on how to find that molar mass? Or if you have found that molar mass, type that answer in the chat so that we can check our answers, make sure everyone's understanding. Let me know what you guys get. I'm going to give y'all about a minute to figure that out. And about 10 seconds in, I'm going to start solving it. So if you get stuck finding that molar mass, you can check your work on the board. All right, so I see that I have 9 carbons. And looking at the periodic table, the molar mass for that is 12.01 grams per mole. Again, you might have something a little bit different. As long as it's in the general gist or whatever your teacher gives you, that's what you should go off of. And then H, we have 18 of those times 1.01 gram per mole. And now we just multiply across, we get 84.09 and 18.18. And then if you have multiple elements like in this one, you're just going to add them together to find the overall molar mass. So I'm going to give you all about 10 seconds to add that together. I always think it's great to get practice with the calculator you're going to use on tests, because I know if you aren't familiar with a calculator, it's kind of hard and can take up time that's important to answer the questions on tests that you take. So getting that, we should have got 102.27 grams per mole for that C9H18. If that's what you got, you're absolutely correct. So we're going to go back to this. And now we need to get from that grams of oxygen to milligrams of C9H18. So first, we're going to go from grams to moles using that molar mass we just found. And if anyone can beat me through this calculation on your own piece of paper, type that answer in the chat so that we can check answers and make sure everyone's understanding. So we know 1 mole based on this molar mass that we found right here. We know 1 mole of oxygen has 32 grams. Now, this is O2, moles of O2. We're at moles of oxygen, and we need to somehow get to moles of C9H18 so that we can get to milligrams of C9H18. So to do that, we're going to use those coefficients in that balanced chemical equation. That's why balancing that equation is so important. So we do moles of O2 to moles of C9H18. And then we just look at those coefficients directly from the problem that we balanced. So we see we have a 2 here and a 27 here. So we're just going to match those to our corresponding ones. So 2 for O2 and 27 for C9H18. And then we are going to go from moles of C9H18 to grams of C9H18. I'm going to start a new line just because we're running out of space. But I put moles at the bottom, and then at the top, I'm going to put my grams of C9H18. And based on what we calculated, we have 102.27 grams for 1 mole. And then last, since this problem's asking for milligrams, we need to go from grams of C9H18 to milligrams. So I'm going to do grams of C9H18 to milligrams. And if anyone knows that conversion, I encourage you, type that in the chat. See how our memorization is or how our skills are. Type that conversion in the chat. Got 5, 4, 3, 2, 1. All right, if you said 1 gram has 1,000 milligrams, you are absolutely correct. Great job. And now the reason I set this up the way that I do is because now you can just go through and multiply the top and divide the bottom. So when I put it in my calculator, it's going to look like 60 times 27 times 102.27 times 1,000, running out of space, over 32 times 2. And it just makes it really easy to kind of do my calculations. So I'm going to give y'all about a minute to put that in your calculators. All right, if you got 2.59 times 10 to the 6th milligrams of that C9H18, you are absolutely correct. Great job, guys, in that scientific notation. I've ran through it a lot, so I'm not going to go over how to find it unless someone needs help. So I encourage you, if you're struggling with scientific notation, type that in the chat and I will run through how to do scientific notation, how to find it. So that concludes our first problem. If you're just now joining, it is so great to have you. Thank you so much for coming to Chegg's Stoichiometry Office Hours. They're here to help you be successful in all of your classes, and then they have Stoichiometry Office Hours every Wednesday and regular office hours all week long for different classes like chemistry, organic chemistry, calculus, whatever you need help with. Chegg is your source to help you with your classes. I encourage you throughout this live stream to comment and ask questions that you have. These can be questions from your homework, questions that you went over in class that you want more clarification on. Whatever it is, I'm here to help and I would love to help. So ask those questions. That's what these office hours are here for. All right, now we're going to move on to the second question. We had a lot of questions about it last week, and it's ICE tables. So if you're in that Chem 2 or some like upper level Chem, you've probably seen this. I don't know if they do it at entry level Chem at most colleges, but ICE tables are very important to chemistry. They tell us how fast a reaction is going to occur and what it needs for that reaction to occur. So I'm going to do a quick little overview before we start because I want everyone to kind of conceptually get it. This is going to take about 2 minutes. So we make ICE tables when we're dealing with the rate of reaction. What ICE tables tell us is the I stands for initial value. This can be a concentration or it can be a like pressure. So we see ATMs, pascals, things like that. C is for change. So how is that concentration, how's that pressure changing throughout this rate of reaction to get to equilibrium? Rate of reactions are also all about equilibrium. So equilibrium is going to be what that concentration and ATM are at when the reaction is kind of complete and just standing still and peaceful. That's what equilibrium is. Change. Now, for the purpose of the problems we're doing tonight, when we speak change, we're talking about subtracting reactants. So reactants are going away and products are being added. Now, this won't be the case all the time, but for like chemistry to everyone as a general kind of just minus is reactants, plus is products. So that's kind of our overview. Oh, and then one more important thing that we'll be dealing with is K. K is the rate of reaction constant. It's just important. It's a constant that's going to give us all the information we need to know about the rate of reaction. And you find that by doing your concentration of your products to an nth power, which we'll go over when we see the problems, over your concentration of reactants. And if anything I'm going over when talking about this isn't making sense, please type that in the chat and I will go over it in more detail. I'm here to help, so any questions you have, ask them. So the problem that we're going to be dealing with specifically is what are the partial pressures of the gases in a mixture that starts with 3.21 atms N2 and 6.21 atms of O2. ATM stands for atmosphere. If you haven't got there yet, I know when I started chemistry, I just memorized the symbols and I didn't know what they actually meant. And then we also have a K value, which is our rate of reaction constant, which is going to be very important to us. So also, the problem provided us with a balanced chemical equation, which is always nice. It's always nice to not have to balance your own chemical equations. So we're going to write our I, C, and E. You don't have to do this, but for organizational purposes, I think writing them out is very, very important. So then we're going to write the initials that the problem gave us. So we start with 3.21 atms of N2, and we start with 6.21 atms of O2. Then, since our problem doesn't tell us whether or not we start with any of that N2O, dinitrogen monoxide, we're just put a 0 there because we don't start with anything and we don't know that we start with anything. So we can just assume that we have no dinitrogen monoxide. Now, what we're going to do is the change. So when we're finding change, coefficient is extremely important. So if the element we're looking at has a coefficient that's not 1 around it, that's going to be very important. So remember, we're subtracting reactants. Reactants are going away because you can think those reactants are going away to make the product. If we're starting with no product, equilibrium is going to have some sort of product. So we know reactants going to have to go away to make that product that we don't start with. So that's why we use that subtraction sign. And we're just going to do minus 2 for that coefficient that we see right here. And then X. X is the variable of change that we don't really know what it is. And then for oxygen, it's just going to be minus X. It's minus because it's a reactant. So that reactant has to go away to make the product that we don't start with because there is product in equilibrium. And that no coefficient because our coefficient on O2 is just 1. And then last but not least, the change for that dinitrogen monoxide is going to be plus 2x. The reason that is we have that coefficient of 2, so it's a 2. We start with no dinitrogen monoxide, but we end with some, so we know we're going to have to add that product. And then our E is actually the easiest column to fill out. We basically just go down on each of these columns and we just write it side to side. So 3.21 minus 2x, 6.21 minus x, and then just 0 plus 2x, or you can just write 2x, which is what I will do. Just write 2x. Okay, now we talked about this briefly. I'm going to erase this so we have enough space, but we talked about this briefly. K is products over reactants. So for writing out K, we can do K equals 2x over 3.21 minus 2x. Oh, I almost forgot something. Now, that coefficient comes into place again because we have to write a squared. If the coefficient is not 1, there's a squared. That's why I think we wrote over here to the n power. N is whatever the coefficient is. That's the power of what's in the brackets. So we do that squared. And then on the bottom where we have 3.21 minus 2x, that'll also be squared. And then 6.21 minus x. All right. So now we need to find out what x is, and we can do that because the problem gives us what k is, which is 3.21 times 10 to the negative 28th. 3.21 times 10 to the negative 28th. So this math is a little bit confusing. I think we can all admit what we would do if we had to solve it manually. So it's gonna take a lot of algebra manipulation, but that top would be 4x squared because we'd square the 2 and the x, so it would be 4x squared. Now, the bottom, we would have to do our like front goes with front, middle with front, back with front. We'd have to do the FOIL method if y'all have learned of that. Now, most teachers I know would give us nice, easy numbers. If your teacher does not give you nice, easy numbers, you will need to know the algebra of this. But since this is more of chemistry, I don't really want to waste time going through the algebra as it would take like 7 to 10 minutes. What I'm going to do is give y'all about 2 minutes to try to start to solve that or find a way that you could solve it. So when I did these practice problems, I would use some sort of math calculator that would be able to solve it really quickly for me. So that's what I would encourage you to do. But you've got about 1 minute and 30 seconds to try to think of how you would solve this if you were given it. All right. So for me, I'm just using that photo and like putting that into a math calculator. So that's what I would encourage. You've got about 1 more minute. All right, about 30 seconds, guys. All right, about 10 more seconds. Okay, since these calculations are so precise, if you got anywhere in the ballpark of 6.02 times 10 to the negative fourth, anywhere around that, it could be a little less, a little more, that is what the answer should be. Again, teachers are pretty lenient. I know mine, if I could get to this step, I was good with it. But now we have one more step that we need to do. This is asking for those partial pressures of the gases in the mixture. So we solved for X when we were like doing this algebra problem. We solved for X. Now we need to go back into each of these individual E's to find what the partial pressure would be at equilibrium. So we plug it in. We have 3.21 minus 2, and then what did we determine that was? 6.02 times 10 to the negative fourth. All right, so let's put that in our calculators. I'm going to give y'all about 30 seconds for that one. And you should have got about 3.21 again. One thing about these problems is that they do tend to give the same equilibrium sometimes as they did initials, and that kind of depends like what your teacher will want you to do with that. If we look at the second one, we have 6.21 minus x. So if we do 6.21 minus 6.02 times 10 to the negative fourth, we're just going to get that 6.21 ATMs again. And that's ATM of, I guess I should be better at labeling, of O2, 3.21 ATM of N2, and then 2 times 6.02 times 10 to the negative fourth, which if we put that in our calculator, we should get about 0.0012 ATMs of N2O. So that's the answer to that problem. I know that one was a little bit confusing. The math was a little bit complex, but if you have any questions about the problem, put them in the chat. I'd be more than happy to answer them. If you're just now joining us, it is so great to have you. I'm Allison. I'm the instructor for Cheg's live office hours for stoichiometry. We are doing some problems that I've prepared right now, but I would love if you type those in questions in the chat. That's what I'm here for, is to answer whatever questions you have and whatever you're wanting to know, whether that be a homework problem, something you discussed in class. I would love to answer that for you. We have a little bit over halfway left. So I'd really encourage you, ask those questions so that I have time to answer all of them. All right. Now, we touched on this a little bit last week, but we are going to do another limiting reactant problem. I picked the long questions to go over today, but the long ones are normally tend to be the hardest. So that's why we're doing those long ones. I feel like y'all are getting advanced and learning stoichiometry more, which is so good. That's what I love to hear. Again, if you know anything that I asked throughout this, I encourage you to answer and type your answers in the chat so that we can check our answers and make sure everyone is understanding. So, what is the limiting reactant if we start with the same amount of reactants below? So we have N2, O2, and N2O. I kind of just copied that chemical equation we balanced earlier, so we can balance it the same way. We've already been through some balancing, but if you're struggling with balancing still, type those questions in the chat. I'll work through it more so that we can all understand. So we have 2 N2, 1 and 2. And you can check it. We have 4 N's, 4 N's, 2 O's, 2 O's. So we know that that's balanced correctly. Now, we want to find out the limiting reactant if we start with the same amount of reactants below. So by same amount, we mean same amount of grams. So we can pick any number. I picked 10. 10 is always super easy, I think. So I'm going to start with 10 grams of N2. 10 grams of O2, and we need to find the molar masses of each of those. So our molar mass for N2 and O2. I'm going to give y'all 30 seconds. These are pretty easy molar masses. You have 30 seconds. Tell me what those molar masses are. Let's test your skills. Can you guys find the molar masses of these two? Got about 15 seconds. Five, four, three, two, one. All right, come on, guys. 2 times 14.01, 28.02. If you said that, you are absolutely correct. Great job. Oxygen, 2 times 16. If you got 32 grams per mole, you're absolutely correct. Great job. Now, Let's go from grams to moles. So we need to go to our moles of N2. And if you weren't on the live stream last week, the purpose of limiting reactants is we're trying to find out which of the things we start with is going to limit how much product we can make. Because there's always one of them that keeps us from making more product. That's the limiting reactant. And then there's the excess reactant, which basically is like let us make an infinite amount of product. So we have 1 mole is 28.02 grams, we said. Then we had 1 mole is 32 grams down here. Now, what we need to do is we take all of the reactants to one product. Since this problem only has one product, it's easy. We have to take it to figure out what limits the product. But if you had 2 products when you were doing a limiting reactant equation, what we would do is choose one product to take both reactants to. So I'm going to go moles of N2O, or moles of O2, can't write, to moles of N2O, moles of N2 to moles of N2O. And the reason we write it this way is whatever's on the top, we want to cancel on the bottom so that we can end with what we want. And in this case, we want moles of N2O on both cases. So then to get these coefficients for the moles of N2O, moles of O2, moles of N2, we go to our balanced chemical equation like we did in the problems prior. We get 2 moles of N2O from right there, 2 moles of N2, 2, and 1. If you have any questions on where I got that, let me know in the chat, and I would be happy to go over it in more detail. All right, now you guys have 1 minute to figure out what the answer to this problem is. What's the limiting reactant and how many moles of the N2O am I going to make? And we got a quick question from YouTube. Are organic compound structures real or not? Short answer, yes, they are real. There's lots of science to back them up. They've done lots of testing to determine if they're real. Some of the more specific stuff in organic chemistry, not 100% sure, but I would trust scientists for the most part, I would say. So y'all have got about 30 more seconds to solve this problem. Once you know those answers, type it in the chat. See if you can beat any of your peers or beat me to solving it. All right, about 10 more seconds, guys. 3, 2, 1. All right, what we are putting in that is in the calculator, we go 10 times 2 divided by 28.02 divided by 2. We should get 0.36 moles of N2O, just rounding a little bit for sig fig purposes. It could even be 0.4. And then the bottom, 10 divided by 32 times 2 should get 0.625. So what's the limiting reactant? You got 20 seconds. Type it in the chat. Tell me, what is the limiting reactant based on this information that we just found out? Five, 4, 3, 2, 1. Whatever makes the least moles of product is the limiting reactant. There's the least amount of moles of product. N2O, 0.36 moles of N2O is less than 0.625 moles of N2O. So we know N2, I'm going to write it down here, N2 is our limiting reactant. So I see a comment from Momin. The state is not mentioned for N2O. It's not in this problem because state doesn't really matter for N2O. But when we get into our rate of reaction, like the problem above, it is important to know the state. But for this, I would say dinitrogen monoxide is a gas, but don't quote me on that. But the state's not really important for our limiting and excess reagent problems. So we now know N2 is our limiting reactant. So for another new skill we're learning this week, we're just learning all of the new skills. We want to know what the percent composition of each element in the following molecules is. So this is a little easy. I figure we have multiple really long problems. So let's do a short one that is kind of fun, in my opinion. Y'all might not think the same. But we want to find the percent composition of each element in the following molecules. And real quick, before we get started, if you're just now joining the live stream, welcome. It's so great to have you. I'm Allison. I'm hosting this live stream. Throughout the live stream, I encourage you to ask as many questions as you want. I'm here to answer all the questions that you have. I would love to answer any homework problems you have, anything in class that didn't quite make sense, anything about chemistry. I'm fair game. So ask those questions in the chat. Let's find the percent composition of each element in the following molecules. So we have C7H12O3. Now, the first step in this is to find the overall molar mass. What we're going to do is we're going to do A together, B you're going to do on your own. So we're going to challenge you to see how much you have learned from doing A. So pay close attention. So first, we want molar mass overall. To do that, let's see if anyone remembers. I'm going to give y'all 20 seconds. Tell me, how do I find molar mass in the chat? All right, so that overall molar mass, we would do C is 7 times 12.01, so 84.07, H 12 times 1.01, 12.12, O 16 times 3, 48. We've got about 15 seconds. Let's add that together just so I can put that in the calculator and have some time. 84.07 plus 12.12 plus 48 should have got 144.19 grams per mole. If you got that, give me a thumbs up or a yes or something in the comments so I can make sure everyone's following. But now we're going to go to molar mass overall. For that, what we would do is we're going to we see the molar mass of each of our individual components. We just found those. That's why I set it up this way, because it's going to make this problem super easy. If we start with carbons, we do the molar mass of all of our carbons, which we determined to be 84.07. If I'm moving too fast or you're not understanding something, type in that chat. I'd be more than happy to answer for you. So we're going to do the mass of the elements over the mass of overall. So over 144.19. Since it asks for a percent composition, we're going to do times 100%. So I'm going to give y'all 30 seconds. Put that in the chat. Let me know what you get. All right, 10 more seconds. 3, 2, 1. If you got 58.3%, you are absolutely correct. Great job. Now, how would we find the percent composition for hydrogen, or what is the percent composition for hydrogen? We would do H equals 12.12, so the mass of the elements over the overall mass times 100%. Put that in the calculator. You've got 30 seconds. If you said 8.41, you are absolutely correct. Great job, guys. Let's see if y'all can do this last one. Oxygen, mass of the elements over overall mass times 100%. Put that in the calculator. Should have got 33.29%. And a way we can check is we add all those percents together, and if we got around 100, we are correct. So let's see. Adding them together, I got 100, just so everyone can see, 100.0, so I know that I am correct. So that's how we find the percent composition. Does that make sense to everyone? We're going to come back to this, but first I want to answer this question from Lindsay on TikTok. When do you use the quadratic formula with the ICE method? So I think we have, we're about to use the quadratic formula. And from Mar on TikTok, can you do KEQ calculations with exponents? We're about to do that too. So y'all came just in time. We're about to answer both of those questions. I'm going to skip B for percent compositions for right now, just so we can get those questions answered and everyone can understand ICE tables. But for now, remember how to do percent compositions and we'll come back. But I want to get everyone's ICE table questions answered. So we're going to learn when to use the quadratic formula with the ICE method and doing KEQ calculations. All right, so for this problem, we have 2.5 moles of HI was injected into a 10.32 liter vessel at 25 degrees Celsius. What is the hydrogen molarity for the reaction? And it gives us the balanced reaction, and it also gives us the KEQ value. So we put our ICE, we have I, C, and E. So earlier I said I stands for initial, C for change, E for equilibrium. We start with I. I is what we start with. What we want to do is find our molarity. This is kind of a trick question. Since the ending problem's asking for molarity, we have to start with molarity. To do that, we do our 2.5 moles over 10.32 liters. If you got 0.242 molarity, you're absolutely correct. So that's going to go in our initial. And then since the problem doesn't say what we start with regarding products, we assume that's 0 because we don't start with products. Most of the time when we're doing a chemical reaction, we don't start with any products. Then we're going to do change. Based on that coefficient, change is going to be 2x, 1x. Reactants we subtract because the reactants are going away to create products. So we do a minus sign, and we do minus 2x because of that 2 coefficient. For products, we're going to do plus because we're adding products. We're creating products, so that's what the plus means. Just plus x for both since we have no coefficient besides that 1. And then E for equilibrium, we just go straight down. So 0.242 minus 2x, x, and x. And then now let's get to those KEQ equations. So we have K equals products over reactants. So K equals the concentration of X over concentration of X times or over 0.242 minus 2X. And we're going to square that. The reason we square that is since there's that 2 coefficient again, we have to square the reactants. I don't know the specifics in that. I'm sure there's some testing that can be done to show why we square that. But I do know it's a rule of rate of reactions in KEQs that we do 0.24 minus 2x squared. Now, for our K, we have 0.1. We have 1.26 times 10 to the negative 3. I always find it's easier just to write it in regular form and not in scientific notation when it's just that small. Okay, now we want to figure out, so this is the KEQ calculation with exponents, and then we're also going to use the quadratic formula. So what I'm going to do is I now want to solve for x. We're going to do a little algebra. What I'm going to do is x times x is x squared over 0.242 minus 2x squared equals 0.00126. And I'm just simplifying. If you get confused on any algebra, type that in the chat in the comments, and I would love to explain better in detail algebra. I have some tutoring experience in algebra and calculus, so I'd be more than happy to help. Now we're going to do the FOIL method with this 0.242 minus 2x since it's squared. I find it easier to write it out, to do FOIL method, writing things out. So I'm going to do first times first. 0.242 times 0.242 is 0.058564. Then I'm going to do first outside. So 0.242 times minus 2x. So 0.242. 0.242 times 2. So I get minus 0.484x minus 0.484x because I'm just doing the inside and then the last. So what I need to do is 4 plus 4x squared, double negative. Now I'm just going to simplify that before I put it back into my fraction. I can combine those 0.484s. Goodness, I can't talk. And I get 0.968. So my final fraction before doing more simplification after foiling is x squared over 0.058564 minus 0.968x plus 4x squared. I know you guys are loving this. And then what we're going to do is that's equal to 0.00126. Now, next what we're going to do is we have to multiply all of this over. It's a lot of algebra, lots of simplification. It's really easy to mess up these problems, but if you're careful and write it out step by step, I think you're going to be fine. So we do 0.00126 times 0.05085664. And we're going to get, that's going to be 7.00000738. And then we'll do the same for this one. So minus 0.968 times 0.00126 should have got 0.00122. So minus 0.00122x. And then just that 4x squared times that. So 4 times 0.00126. We're going to get plus 0.00504x squared. I know it's a lot of exponents, lots of that, but we are almost done. So we have an x squared on the left. We want to get 0 on the left to be able to use the quadratic equation. So we're just going to subtract that x squared on both sides. So finally, before putting into the quadratic formula, we get 0. Oops. Let's erase that. Equals 0.000738 minus 0.00122x minus 0.99496x squared. Now we are finally ready to do the quadratic formula. I'm going to write it out just so we know what that is. It's x equals negative b plus or minus the square root b squared minus 4ac all over 2a. That's how we're going to solve for x. This is a, this is b, this is c. So now let's write that in. We have x equals 0.9946 or 496. Whoops. And it's because those negatives are going to cancel out. Plus or minus the square root of, oh wait, sorry guys, I already messed up. Told you I was a lot of fun math. I used a, this should be b, 0.00122. Plus the square root of 0.00122 squared minus 4, negative 0.99496. and then times C, 7.0000738. So that's our x equals negative b plus or minus the square root of b squared minus 4ac. And then now 2 times negative 0.99496. That's A. Now we are going to put that in our calculators. So I'm going to give y'all about 45 seconds to a minute to put that in your calculator. Let's see. Want to check and make sure it's right. How did I get from 0.0054x squared to 0.99496 squared? The way I did that is I subtracted a 1x squared. So I did 0.00504x squared minus 1x squared. And that's how I got that 0.99496. Does that make sense? Maybe? Yes, it is an ice table from James on TikTok. Okay, we're going to have to solve this the old-fashioned way. So I'm just going to write what I'm doing for 884 times 10 to the negative 6. What I did is I solved this right here to put there. If you aren't given a calculator on a test, this is what you'll be doing. And then we have 4 times 0.99496 times 0.0000738. And that will be plus, the reason that's a plus is I have a double negative, 2.94 times 10 to the negative 4th. So putting that in the calculator, 5,14844. Sorry, this math's a lot, but this is how you would use the quadratic formula if you're not given a graphing calculator. And then we would want the square root of 0.000295. I was not given a graphing calculator when I did this. I had to do it by hand, which was no fun, but it's okay. We got to work with the tools our teachers give us. So what that would end up being is 0.00122 plus or minus 0.017 over 2 times negative 0.99 which is 1.988. And then we'd put this in our calculator one last time. Is everybody following? I know this math's really complicated, but hopefully it's getting through the nitty-gritty details of an ice table. So we'd put that in the calculator. I'm going to tell y'all now, since the denominator is negative, we need the top to be negative so that we can end with a positive answer because our x can't be negative. That's another rule of rate of reactions. We had 0.00122 minus, we're going to do minus 0.017 over negative 1.988. So let's put that in the calculator. And finally, we have an answer as to what x is. X is 7.94 times 10 to the negative 3. I know that's a ton of math, but is everybody following along? Is everyone following along? I know that's a ton of math, but we eventually got, after all of this lovely math, x was 7.94 times 10 to the negative 3. If you have any questions, I would love to answer them. I know that was a lot in one problem, and we want to find the final molarity of H2 for this. So what we would do is, since we know X is 7.94 times 10 to the negative 3, and our final molarity is just X, our H2 final is 7.94 times 10 to the negative 3. That was a super long problem. Yes, this was an equilibrium problem and an ice table and the quadratic formula all in one. Took us all of this purple to solve, but I'm proud of us for all sticking through it. Does anyone have any more questions on this problem? I know it was pretty difficult, but I would love to answer it. I'm going to give y'all about 20 more seconds to ask any questions you might have. So just to clarify, we did our ice table, which was right here. Found that molarity for the initial value, set up our K equation. All of this right here was solving that K equation. And then here was finding what the problem asked for, which was that H2 molarity. So if there's no more questions, we'll move on to one last problem. We're wrapping up. We have about 4 minutes left of this live stream. So if you have any questions, this is your last chance to ask them. If not, we'll do one more problem I have of my own. So without any questions, let's do this percent composition problem. So we have FeSO4. Hopefully it'll be like a breath of fresh air from that long, complicated problem we just did. We want to, we have how do you find the pH and pOH from an equilibrium ice table? We find pH by doing negative log of H plus. And we find pOH by doing negative log of OH minus. Those are the only ways I know that they show to do pH and pOH. I would think you'd have to have H plus or OH in that table present to find pH and pOH. You could, though, do an educated guess based on what you're given. So, like, since I know that this is starting with HI, which is a strong acid, I would guess that the pH is more acidic, but you would probably, I think, have to do no H plus or OH minus to find out pH or pOH from Avoid321 on TikTok. Hopefully that answers the question. If you have any more, please ask them. Okay, for the percent composition of FeSO4, I'd write out, first I need to find my overall molar mass. So Fe equals 1 times, does anybody know that molar mass of Fe? I'm going to give y'all about 15 seconds to put it in the chat. 4, 3, 2, that was definitely way quicker than 15 seconds, but it's 55.85. So we'd get 55.85. S is 1 times 32.07. O equals 4 times 16, which is 64. Let's add those all together. If you got 151.92, you are absolutely correct. Great job. And then those percent compositions. So we do O for Fe, we do overall of Fe, so 55.85 over 151.92 times 100%. Put that in the calculator. And you should get 36.8%. If you got that, great job. For S, we get 32.07 over 151.92 times 100%. Put that in the calculator. And we get 21.1%. And then last O is 64 over 151.92 times 100%. And we get 42.12. Add those all up and you get that 100%. That concludes our office hours for today. It's so great to have you. I'm so glad that you came. I encourage you to join other live office hours throughout the week. And thank you for joining this one. Come back next Wednesday at the same time to learn more. We'll work through more ice tables, more weighted reactions. So I encourage you to join. Thank you so much. Bye, guys.